Hey everyone, Mr. Palmer here with Lesson 5 on radioactive decay and half-life. Just wanted to review Lessons 2 through 4 so that we're fully prepared for this lesson. In Lessons 1 and 2, you looked at the properties of the nucleus, the mass of a proton, mass of a neutron, our nucleons, and how they contribute to our binding energy using E equals mc squared. That binding energy curve in Lesson 3 is quite important as we look at the stable nuclei and that stable nucleus band, and it leads to the radioactive decay of fission as well as the process of fusion to get to stable nuclei around iron 56. In Lesson 4, Stephen looked at the details of radioactivity at alpha decay, which is used in our smoke detectors, beta decay, emitting electrons, often in carbon decay, and gamma decay to get to a lesser energy state, more stable. To introduce half-life, let's look back at the alpha decay of our smoke detectors with the radioactive nucleus of americanium. Now, we know we have to change the batteries in a smoke detector, but do we have to change out the radioactive sample of americanium? When we look at the process of the alpha decay, or in this case, the beta decay of a carbon-14 atom into a nitrogen-14 atom, the process is random. Each individual nucleus decays independently from any other nucleus. Just because one nucleus has decayed in image B doesn't mean that it affects any further decay in image C. That rate of decay is proportional to the number of nuclei present, and also proportional to the time interval involved. If there are more nuclei present, there's a greater probability that some will decay. And if you measure over a longer period of time, there's going to be more decay there as well. This is all summed up in the decay constant, represented by the Greek letter lambda. The larger the decay constant, the more radioactive the isotope, so that the probability of decay is increased. Remember, it's a random process, so some nuclei may decay faster, some may decay slower, but the decay constant does give an average representation of that nuclide. As the radioactive sample decays, the amount of remaining undecayed nuclei is given by this equation, which was derived using calculus but can be solved with exponential functions and natural logs, which you guys have seen in pre-calc or maybe even algebra 2, and it's used in sample problems later in this lecture, so you guys can get some review there. Now, as you can see, the number of nuclei does decrease over time, which makes sense with radioactive decay. But if you look at the rate of radioactive decay, the slope of this line, it is also decreasing over time, and we call that activity. The activity is the change in nuclei over the change in time. It's the slope of that previous graph, which, what do you know, is the same shape, the beauty of exponentials. We can calculate that exponential by multiplying the number of nuclei times the decay constant, and it winds up with the same exponential function, very similar. To make this math a little simpler and sometimes avoiding the exponential and natural log mathematics, we can look at some patterns, and that pattern that we're going to highlight is the half-life. So looking at this graph of carbon-14's decay, if we start with 100% of a sample at time 0, we can see that decay curve over time, and it will decrease to 50% of that sample after one half-life. That's our definition of the half-life, the time it takes for the sample to have the undecayed atoms. So 100% decays to 50% in one half-life. In another half-life, that 50% decays to 25%. Third half-life, 12.5%. Fourth half-life, 6.25%, and so on. This is true for any radioactive sample. In the case of carbon-14, you can see at the bottom of the page, the half-life is 5,730 years. But how do we come up with that? The half-life can be calculated using that decay constant, dividing it into the natural log of 2, since this is the half-life after all. This equation is really helpful when you have a graph and you can measure the half-life when it gets to 50%, and you can use this to then calculate the decay constant. Or, if you know the decay constant, you can calculate the half-life. So let's put this to good use with a practice problem. The sample activity problem is found on page 930 of the G. and Coley textbook if you want to follow along. I'm going to try to type the answers here, but it certainly isn't as smooth as following along with the textbook. So the isotope carbon-14 has a half-life of 5,730 years. If at some time a sample contains 1 × 10 to the 22 carbon-14 nuclei, what is the activity of the sample? All right. So what we want to use here is that the activity equals the decay constant times our number of nuclei, all right, which they gave to us. However, in order to do that, we have to figure out that decay constant. All right. So the decay constant equals 0.693, that's the natural log of 2, divided by our half-life, all right, which they give us as 5,730 years. So 0.693 divided by 5,730, you guys can tell this is going to be a really small number. Okay, that can then be plugged into the top equation here, multiplying by 1 × 10 to the 22 to get your final answer of 3.83 × 10 to the 10 decays per second. Another practice problem can be found on page 931 in the G. and Coley textbook, example 30-8. We have a sample of radioactive nitrogen-13, sample size of 1.49 micrograms, that's 10 to the negative 6. And nitrogen-13 has a half-life of 10 minutes, which we quickly convert into 600 seconds. This is nice because it has a couple more parts of a problem, A, B, C, and D. So based on the 1.49 micrograms of nitrogen-13, we can use its molar mass to find out how many nuclei are present initially. Then, using the half-life of 600 seconds, calculate the activity. After that, use our equation, our exponential equation, to find the activity after 1 hour. And D, after approximately how long will the activity drop to less than 1 per second? That's just going through half-life, half-life, half-life until that's less than 1. All right, those steps can be found on page 931. It's a bit too complicated for me to type out on my computer here, so check that out in the textbook. All right. A decay series follows the different isotopes that are created with radioactive decay. All right, so here we've got radium-222 undergoing alpha decay to form polonium-218, another alpha decay to form lead-214, beta decay to form bismuth-214, another beta decay to go through its process. All right, so due to these decay series, we can create nuclei that otherwise would not exist in nature. They can only exist through this radioactive decay. Now, what does this look like as we refer back to lesson 3 and the stable nuclei band? If you guys can recall that, let me scroll back up to find that from the previous lesson. Here. All right, so here's our stable nuclei that diverges from n equals z, the slope of 1. And you can see that heavier nuclei require more neutrons to be stable. But what if we're not on that stable band? What if we are radioactive and we are going to conduct radioactive decay series? This is where we're going to wind up, okay, back in this stable band of nuclei. So let's look for example, at uranium-238. Okay, how do I know it's uranium-238? On the bottom is my atomic number, Z. So element 92 is uranium, and when I look at the isotope of its atomic number, going up, I've got 238 nucleons, both protons and neutrons, in that isotope. So we're starting at the top right corner at uranium-238. This is an unstable nucleus. This is an unstable atom. So following this decay series, it's going to undergo an alpha decay. In that alpha decay, we lose a helium nucleus, 2 protons and 2 neutrons. So I go from an atomic number of 92 to 90. Okay, so that's going to be thorium. And I also got rid of 2 neutrons, so a total of 4 nucleons. So from 238 to 234. So uranium-238 becomes thorium-234. The next step then is a beta decay to become palladium-234. Another beta decay to become uranium-234. So that alpha, beta, beta comes back to uranium, but now instead of uranium-238, it's uranium-234. Okay? That undergoes alpha decay with a half-life of 2.5 times 10 to the 5 years. All right, so that alpha decay takes a long time to happen, but it will happen. Okay, it's sometimes it happens really quickly, sometimes it happens really long. Remember that half-life is a probability statistic to have the sample of uranium. That then goes through thorium, radium, radon, and into the bottom left corner of these alphas and betas. All right, these are super helpful to see what the pattern of decay would be and what the daughter nuclei of such a decay would become. Okay, using the periodic table of elements, using our knowledge of nuclei number, okay, protons and neutrons inside that nucleus. All right, so pretty useful. But where is this useful, right? Why are we learning the math of radioactive decay and measuring sample size and activity? Well, remember back to our original example of the smoke alarm. If we've got, while we do have to replace batteries, we don't have to replace the radioactive element in there because its half-life is so long that as it decays to half its population, a quarter, 12.5%, 6.25%, 3.125%, it's still effective at those lower sample levels. The activity is still high enough that it's able to read. However, there will be a certain point, thousands and thousands of years down the line, where that americanium sample is not active enough to give a good reading. So while we've been able to use radioactive elements for purposes in smoke alarms and other uses, we've also been able to use this knowledge and our measurements as a form of radioactive dating. No, this isn't matchmaking service for radioactive elements. It's a way to determine the approximate age of a material based on the amount of sample left and the rate of activity. Well, the activity is the rate of decay of that sample. This video does a really nice job explaining the details regarding carbon-14 decay and how we can determine the age of once living materials. So hopefully you've already watched the video and this should be old news. But your carbon-14 to carbon-12 ratio is relatively constant due to the creation of carbon-14 in the upper atmosphere. And all living plants create that exchange of carbon, so it's the same ratio that we know. And animals eat plants, so that same ratio is the same for all living materials. It's about 1.3 times 10 to the negative 12, carbon-14 to carbon-12. Now, once that living material dies, there is no replacement of that carbon-14. So as it decays, the half-life of 5,730 years takes place, and we can start measuring half-lives until it gets to a measurement that we're not able to measure with our current tools. That's about 60,000 years. So the video said 50,000 years. Whatever the case, it's relatively recent history in the life of the Earth and other living fossils. So how do we measure the life of fossils that are older than that? Well, we have to look at the rock that it's fossilized in. And if that rock has radioactive elements, such as uranium-238, that has a much longer half-life, and we're able to measure much older rocks on Earth. There's a bunch of other radioactive elements that we can use to do this, and it has been super duper helpful to measure our geologic timescale, and maybe even the geologic timescale of other rocks on other extraterrestrial surfaces. All right. Last slide here, guys, is a practice problem from page 934 and 935 in the Giancoli textbook. Dating an animal bone fragment. Again, we have a carbon mass of 200 grams, using the molar mass to find out how many molecules that is, using our activity to figure out our half-life, and plugging that into our exponential equations to find what is the age of that bone. All right, work is shown on page 934 and 935 to follow along, and you also have your radioactive decay lab using FET to become more comfortable with this. and get ready for our test on June 6th. Good luck!